Hello, welcome to the Cmi VFX training tutorial flocking system in Houdini. My name is Christian Schnellhammer and I will introduce you in the main principles of flocking systems as well as crowd systems. In this training video I want to show how we can implement a flocking system. A big part of this training will be a theory part about how a crowd simulation works, and the other part will be how we can implement this in Houdini. Let's start with an example of a flocking system. This video shows a simulation of a bird flock I did in Houdini some years ago. I used the POP network with wax operators for the swarm movement, and then I instanced bird geometry on the particle points. This is just a simple simulation with a very simple bird geometry, but the illusion works fine. And each of the birds behaves the same way. They're using a flocking behavior to avoid other birds and trying to fly with the nearby birds, and they are building groups. They are also following an invisible point here in space. They are flying 2 points in space. One is here and the other one is here. And one half of the birds are following the one of the points. The other part is following the other point. Let's show you another example of a flocking system. It's a more complex system. Let's start. This simulation uses the same technique, the same space simulation like the bird simulation, but with some small extensions. The agents, I call it agents. Agents can be vehicles or birds or humans. They are moving on the ground and they are avoiding obstacles and they are avoiding each other. These are just some small simple behaviors, and the combination of these behaviors will result to a more complex behavior. You see here's a wall with a hole, and the spheres are queuing on this wall, and they are searching this point here. This means every of the agents is trying to reach at this point, and they are also queuing on this point. They are building a group around here. Okay, let's show you another example. This is the same base setup and as the crowd example, and what I did here is I removed the ground and added a tube here with an hole on the here. You can see a hole, and they are trying to reach this point here. Let's start the simulation. And now they can move in 3D space because the ground is removed, and you can see that they are queuing on this entrance, on this hole. And if we wait a long time, we see that all of the spheres will pass this hole. This works really fine. This sample demonstrates the modularity of the system we will implement in this training. Our system will be a system where we can combine a bunch of simple behaviors to get an overall complex behavior in simulation. And this kind of simulation, this kind of system is called steering behaviors. Steering behaviors is a is a system introduced and created by Greg Reynolds in 1986, and in this training I'll guide you step by step how to create such flocking systems and autonomous character movements. Let's switch to the next chapter, introducing the concept of steering behaviors. In this chapter I'll give you an overview, what's the idea behind steering behaviors and how they work. The idea in general is to create a complex behavior by combining relative simple and modular behaviors. But what does steering behaviors mean? Just a small excursion in history. Steering behaviors was created by Greg Reynolds in 1986, and it is a model. This model is a way to simulate the coordinate movements seen in birds in flocks of birds or fish. The original flocking model was based on three distinct behaviors. The separation behavior was used to prevent situations where members of the swarm were crowding each other. Alignment was used to steer all elements of the flock in a common direction. And the third behavior, cohesion, steered a single boy to the average position of nearby flock mates. And this flocking system is already the system we have seen in our introduction video, the flocking birds. What are the advantages of steering behaviors? The steering behaviors are modular. It's a modular system, and easy. I think it's easy to understand, and they're easy to implement, and they are expandable. As we have seen the sample, just by adding some small more behaviors, we get a more complex and completely different simulation. Steering behaviors. Steering behaviors consists of agents. Agents are, for example, vehicles or birds or ants, humans. We have behaviors, we have mind, and we have the simulation. The simulation which is updating the positions and the velocities of our agents. The agent. What is an agent? Agent is a single instance of an autonomous character. And it is, for example, a vehicle, a bird, a fish, or a man. Then we have a behavior. What is a behavior? Behavior is a distinct module, and it offers a steering direction. And we have a mind. Let's explain the mind by means of an example. We are standing here, and in front of us there's an obstacle, and we are moving in this direction, and one of our behavior offers a steering direction to the left because we are standing in front of a wall, and the obstacle avoidance is trying to avoid not to collide with the obstacle. Then there's an other man waiting, and one of our behaviors, the separation behaviors, is suggests an steering direction to the right because we have to avoid this person. And now we have a problem. We have two steering directions. The obstacle avoidance is offering turn left, and the separation behavior is offering a steering direction to the right. And now this is the moment our mind comes into the game. Our mind collects and receives all steering suggestions from the behaviors, and it decides what kind of decision has to be made. It decides the final steering direction. Let's see what behaviors are out there. Yes, this is a list of the important behaviors. This is obstacle avoidance. For example, obstacle avoidance is, as the name implies, it is used to avoid obstacles, and then we have a separation behavior. It is used to move away from other agents and avoiding a collision between them. And the arrive behavior is used to arrive or search to a specific direction, specific location in space. We have follow or flee behavior is used to follow or flee from other agents. We have the wander behavior. Wander behavior is behavior just going around in space, no specific direction. We have the cohesion. Cohesion is used to build groups like flocking birds. We have the alignment. Alignment is used go the same direction as the nearby people do, and then we have flocking. But flocking is not really one behavior. Flocking is a combination of three behaviors: the separation, the cohesion, and the alignment behavior. And with these three distinct behaviors, we get a complex flocking behavior seen in our bird flock example. Let me introduce a good resource in the web related to this topic. This web page is from the creator itself, the Greg Reynolds, and you can find the URL to this site. This site is a good resource to. Here you can find all information you need for implementing steering behaviors, and you can find a lot of resources and links to other sites. And for example, let me show you some of the behaviors. Here are some Java applets demonstrating the behaviors. For example, the seek and flee behavior. We have a point, and we have two agents. The green one is searching this point, seeking this point, and the red one is fleeing from this point. Another one is the wander behavior. You can see this behavior uses an algorithm to just to steer around in space in a smoothed way. And another example is obstacle avoidance. It demonstrates how obstacle avoidance is working. We have an agent and a test ray in front of the agent which is testing if there's an obstacle and calculates their respective steering direction. And we have here a queuing example. This is the same sample I showed you in the beginning of this tutorial. The spheres waiting on a wall, and as well as a flocking example. Okay. Let's switch to the next chapter, which is covering some important preparations and planning things we have to do before starting with the implementation of our own flocking system in Houdini. Before we start with the implementation, we have to do some preparations. There's some items we have to give some thoughts. Let's take a look to the obstacle avoidance, for example. The obstacle avoidance behavior needs to know where the obstacles are, of course. We have to know the intersection point from the velocity vector with the polygon face of the obstacle as well as the angle with the intersection. How can we do this in Houdini? Let's take a look into the Houdini documentation, especially in the Vex documentation. Vex functions. Houdini provides us with a Vex function called intersect. And this function computes the intersection of the specified ray with the geometry. We can pass the geometry, we can pass an origin vector and the test direction, and what the function returns is the intersection point. If we have the intersection point, we can compute anything else we need for the behavior. So that is the right way for the obstacle avoidance. Let's continue with the separation behavior. The agent has to know the neighborhood of other agents. Since we have to calculate a steering vector to move away from other agents, we have to know where the other agents are. And the environment around one agent is called neighborhood. For example, imagine a circle and we are standing in the center of the circle, and all agents within this neighborhood circles are from interest for our calculation. All other agents outside of the circle are not from interest because they are too far away, and they do not influence us in our decision where to steer. But how can we calculate the neighborhood? How can we retrieve our neighborhood? There are different possibilities. We could iterate. Let's think all agents are points in the space, and what we could do is iterating through all points and calculate the distance and to test if they are within the circle or not. But this is not really efficient because we have to do this for every point in space, and if we have a lot of points, let's think billion points, we have to do this a billion times for each agent, and this is really not efficient. So we have to do this another way. Houdini provides us with a Vex function called PCOpen. PCOpen is a point cloud lookup mechanism which is very fast and allows us to look up points around a specified position in space. Let's take a look into the Houdini documentation. The function from interest is the PCOpen. The PCOpenVec function opens a point cloud file. We can specify a point in space, we can specify a radius, and what we get back is a handle to a point cloud. By means of this handle we can iterate over all points and import all attributes around us. So the PCOpen needs a file name or an op syntax reference to an op geometry. So we can use this means we can use instead of a file name we can use op and followed by a path to an op geometry. The problem here is this is exactly what we need for a point cloud lookup and for the neighborhood lookup, but the problem is that this only works on op geometry paths and not for particle paths, and this is a problem for us because we can't use a particle network. There are different solutions out there. What we can do is building a dynamic network and using in building our simulation just out of dynamic nodes and a SOP solver. I will explain this in the basic setup later, but first let us write down some important items we need for our implementation. This is called requirements. The requirements are a list of items of things our system can do. It is a guideline for us while implementing our system. Let's open a notepad and write down the requirements for our flocking system in this training. And let's start with one thing what is currently in my mind. It is steering behavior is a modular system, as we learned earlier, and what our system can do is it should keep the modularity of this implementation. This is very important because we want to create complex simulations with just some small behaviors. Modular. Keep the system modular. For example, we could create all behaviors as nodes and connecting all behaviors together with the nodes and creating complex simulations. Let's write down behaviors nodes for each behavior. All things we write down here in our list is a must for our system, and it also helps us not to run into a dead end street because we forgot something. So keep this in mind. The next thing is what we need is a mind, and our system should be able to support different mind implementations. Different mind implementations. Our system should work in 3D space. Let's remember the example at the beginning with the birds flock, and this is a 3D example, and if we have ants on the ground, this is a 2D example. Should work in 3D space, flying birds for example, and should work on a ground plane. It also should work on a hilly ground. Ants, for example. As technical requirements, let's use the obstacle detection. We also checked if this is that this is really possible via the vex functions and the neighborhood lookup. Okay, let's leave these items as our main requirements for this implementation in this training. Once we have our requirements, we have to think about how to implement it, and a good approach is to make some small tests to check if our ideas are really working. We already checked the obstacle detection and the neighborhood lookup. The problem on neighborhood lookup was the limitation of the point cloud to just to work with subpath networks, um, and we have to create a dynamic setup for our simulation. And this is the next step we can do: create a basic dynamic simulation setup to check if this idea is really working, and this basic setup can also be used later as a base setup for our implementation. Let's start with the basic setup for our simulation. The first we need is a dummy geometry. Let's create an initial state for our simulation. To do this, we create a circle object on the ZX plane and scattering some points on it. Okay, let's, it's too much points. I think 50 is okay for now. Okay, this will be the agents in space. It's our initial state. Let's create null here, call it out. This is a good practice for referencing, since if we change something here we have to change our reference to this node and call the node agents. The next thing is we have to create dynamic networks. As I already said before, we have to use the point cloud mechanism for neighborhood lookup, and the limitation is that we cannot use particle networks, and we have to do this within a dynamic network. There are different ways. Let's create a dot network. Let's call it simulation. Our simulation DOP network is empty, and what we need first, we need an empty object and attaching data on this empty object. As object name we can use agents, and on this object we will apply our SOP geometry. This can be done via the SOP geometry node. We can use an external SOP and specify the SOP path, and as SOP path we can use the agents out and attaching it via the play data on the empty object. You see here are now, here's the geometry of our agents. Let's call this agents. Let's call this fetch SOP geometry. Okay, now we want to simulate our agents. What we need here is a SOP solver. With a SOP solver we have the ability to get the last time step of our geometry, modify it, and pass it to the next time step. Let's create a SOP solver. We can use an external SOP and specify the SOP path, creating a SOP network within the DOP network, and call it SOP simulation, and reference this in our SOP solver. Okay, within the SOP simulation we need to fetch the geometry, the last geometry of our of the last time step. This can be done via an object merge and a stamping expression. Let's take a look into the Houdini help, the SOP solver help. You can see the expression we have to use to access the previous time step. This is the node we use as last node for our SOP cooking, and this is the data path is the token we have to use, and this is the path to our dynamics geometry data. Let's use this expression and see what happens. Stamp S, then use the output of our geometry simulation. The out is not yet available. Let's create it. This will be this node. This is our out node. We use as stamping token the data path, and as value we use the path to our geometry. Okay, now we can see we have merged the last time steps geometry into this network. And with this setup, now we are able to, all links we create here is between this node and this node will be the simulation nodes. We can alter this input geometry and pass it into the next time step. Let's test this. Let's call this last time step sub, and let's create a simple test, creating a WOP sub, let's create a turbulent noise, specify position, let's use a 3D noise. We can add it to the current position of the points. Add node and modify the position. Okay, let's use a smaller amplitude. Okay, now we can see we modifying the position of the points, and the next time, this is done in the time step 1, and if I go to the next frame 2, I will use this output as input for the next time step. Let's test this. First, let's fetch the geometry back in our sub network. This can be done via the DOP import. We can import our geometry. This DOP network is simulation, and it does not work because we have to change the import style, fetch geometry from DOP network. Okay, let's press play, and we see that the points are simulating. This is a good practice to avoid particle simulation, and with this setup we are able to create WOP sub nodes which are also using point cloud lookups, because our simulation is within a sub simulation, within a sub network, and this was our goal, and this was necessary for our neighborhood lookup requirement. We will use this setup as our basic setup for our flocking system development, and the next steps we will do is implementing a simple mind, and by and by we will implement the behaviors. And while doing this, I will also explain the functionality of each behavior in detail. Now we have our dynamic setup, our base setup for our flocking system. But different like in a particle network, we have to update the point positions for ourselves. In a particle network, we can setting the rules and adding forces to the particles, and the particle network is updating the attributes and the point positions. And this is what we have to do here manually. How does a simulation step work? Let's take a look to this slide. We have an agent in a specific location, and we have a velocity, and we have also force. This is a force, for example, our steering force, our final steering force. And what we have to do each time step is just adding the force to the velocity. This is the right moment to remember a little bit of vector math. Um, just remember what is a director, a vector. A vector is a direction, and a point is a location in space. And if we add a point and a vector, we just translate the point by the values, by the components of the vector. And if we add two vectors, we just concatenating the vectors, and we get a vector starting on the base from the first vector which is ending on the top from the second vector. And this is what we are doing here. We have a velocity vector, we have a force vector, and our result is in the new velocity. Then the next step we have to do is updating the point position. Move the agent through the space. We have a point position, and what we have to do is just adding the velocity to the point. This is translating the point to the new position. This is but since the velocity is has the unit meter per second, this movement should be done in 1 second. So that's why we have to divide the vector by the frames per second to get the vector just for this time step. And this is quite simple. And let this integrate in our setup. Okay, let's integrate this in our simulation. Let's go into our DOP network and our sub-simulation and remove our test here. And the next thing we want to do is adding a solver here, which is moving our points respective to the velocity and the forces. We will add a new operator type. We will create a steering library with all our behaviors and all nodes we want to implement here in our training. The new operator name will be steer solver. Label will also be steer solver. As network type, we choose a geometry operator, and let's name the library steering OTL. We install the library to scan OTL directories. Okay, press accept, and now we have the operator type properties, and if we go into the code tab, we see there's a predefined function, and every time this operator cooks, this function will be called. Okay, press accept for now, and let's add our new node here, our steer solver, and let us edit the wax function. Let's remember the slides with the particle movement. What we have to do is move the point by the current velocity, and here we have predefined variables. For example, we have the p variable specifying the current position of the point, and we have the v variable, which is the velocity. And what we have to do is just adding the velocity to our current point position. And let's remember we have to divide the velocity by the frames per second, and there's a predefined variable tool called time Time inc is a factor which specifies the time one time step takes. So this is the same as dividing the velocity by the frames per second. Okay, press. We can press test compile just to see if everything works fine here. If you have syntax errors and we see compile was successful, we can press accept. And the next thing we need is we have to create an initial velocity for our points. Let's go to the tab. Let's go into our initial setup for the agents. Okay, let's pin this scene view because we have to switch between this view and our DOP network, and this prevents not to follow the scene view, our network view. Let's show all objects. Okay, here we are scattering our points, and you can add a warp sub here, which is creating an initial velocity direction. Initial velocity. And let's turbolize the velocities using the point position and using a 3D noise, and just connect the output to the velocity attribute. Now we have a velocity. Let's visualize this in the scene viewer. Here we can, by pressing the D button, and let's go to the guided markers tab, you can add here custom attributes. Let's add a new attribute vector. By right click you can choose edit and call this V for velocity. We can set a scale how long the vector should be, and we can override the color. Let's choose for green for our velocity vector. Apply. Now here we have a button where we have a list of all our attributes, and here we can enable our new attribute, and you can see that we have now a velocity. Here we can change the amplitude of our velocity. Okay, now since we have an initial velocity, everything should work like in a particle network. Just press play, we see that the velocity is moving the points around the space. The next thing is we want to add forces to our points. Forces which are modifying the direction of our velocity. Just remember this slide. We have a velocity, and we want the velocity modified by a force. So let us add in the simulation network. Let's reuse our old warp sub and call it force. Let's call it add force, and here we have a turbulent noise, and let's remove this node here and connect the turbulent noise to the acceleration attribute. The acceleration attribute is the attribute which is used as force attribute in the particle network. Let's use this the first time. Let's use this for our force attribute 2, and within our solver, let's edit our vex function. We have to add this acceleration attribute to our velocity. Just create a command here. We can do this via double slash and just comment what this line is doing. Modify particle position, and before modifying the particle position we have to update the velocity. This is really simple. We just have to, the new velocity will be the old velocity plus the acceleration attribute. The acceleration is also a predefined variable in vex. Let's test if everything's working. Okay, compile was successful. Press apply. Okay, we can use the accept instead. This is closing the windows. Okay. Just take a look. Just add a new variable, a new attribute to see our force attribute. Add a new attribute vector. Call it axle. And the point attribute. And use red color for our force vectors. Okay. Turn on the Excel attribute, and the Windows is switching all the time. Okay, you see here that we have acceleration vector here, and if you press start, we see we have to set the solver flag. We see that it's a little bit too fast. Let us slow down the initial velocities. And we also let us add lesser noise. Okay, start again. Yeah, it is too fast. It's too fast to see anything. We can turn off the initial velocity. And here we see that the force is modifying the velocity, and just use another noise because we are using the alligator noise, and this is just in one direction. Original parallel noise is better candidate for this. Now we see our acceleration attribute is modifying our velocities. And now we have created our own particle system and our own solver. Now we can start with an implementation of our first behavior.